Okay, so hello, good morning everyone. Здравствуйте. Я не говорю по-русски, so this talk will be English. Sorry. I may give it in Polish if you like, but probably English would be easier to understand because of pszczoła, pszczyna, and other words. Okay, so I work at Samsung R&D Institute Poland. I'm also a PhD student at Warsaw University of Technology. In my work, I do some low-level system stuff, some kernel stuff. I'm libUSBGX maintainer, so I do also some USB-related stuff in my work. But I do this also on my university as my PhD degree. Now I'm working on some ADB-related attacks. And today I would like to tell you a few words how generally USB attacks evolved from very beginning, from simple autorun scripts up to bad USB 2.0 and other stuff. So the schedule for today. In the beginning, I would like to tell a few words about USB in general, how it works, what are the basic concepts. Then I will focus on plug-and-play philosophy, what it means for us, how it works, and other stuff. Then I will go through three groups of attacks. First of them are related to USB host. It means that we are trying to attack our computer. Second of them are related to USB traffic itself. It means that we are trying to play with traffic or we are trying to take out some data from this traffic. The third one is USB device related attacks. It means that we are trying to attack a USB device. Usually it's a bigger device than a pen drive. Usually it's a smartphone. So that's why we are interested in attacking USB devices. Short summary and a Q&A session. Okay, so generally what USB is about? From a very high level, USB is about providing service. It's the same like the internet. We are trying to provide some additional service to machine where is our end user who would like to use our service. Kind of services are a little bit different than the internet because we have our storage. This is like cloud storage, only the implementation is different. We have printing, Ethernet itself, so we may have a network card connected via USB. We have camera and many other. So how it is done? In internet, we have usually our client-server architecture, and here we have a host and device. Single host may have multiple devices connected. Single device may be connected only to one host. Single device may provide one or more functionalities. It means that the device, like Andrzej told you, is may be composed from multiple functions. So what USB device really is? First of all, it's a piece of hardware. We need some equivalent of network card to communicate in low-level USB protocol. Then we need the implementation of USB protocol itself. And using this implementation, we may provide some additional service to our host. So we may implement some useful protocol. Then we need a piece of hardware which will provide our additional functionality. So for example, for our pen drive, this is the hardware part which allows you to communicate with USB host. This is the USB protocol implementation in the MCU. This is implementation of mass storage protocol. And this one is a flash memory which you can find in your pen drive. So how we communicate with our USB device? In internet world, we may have multiple services running on the same physical machine with the same IP address. In USB device, in USB world, each USB device also has its own unique address and may provide multiple functionalities. So we have to distinguish between them. That's why we have some kind of equivalent of ports from the Ethernet world, which are called endpoints. Single device may have up to 31 endpoints, and each of them has also a unique address. Endpoint 0 is the only one which may transfer data in both directions. It's also the only one which is mandatory to have by each device. All other endpoints may transfer data only in one direction. And because USB is host-centric, we mark this direction always from host perspective. It means that if endpoint has an in type, it is capable to transfer the data from device to the host. If it is out type, it means that it is able to transfer the data from host to the device. In internet world, we have generally two types of ports. We have TCP and we have UDP. If you are streaming video or doing some high performance stuff, we are using UDP. If we want reliability, we will use TCP and additional protocols. In USB world, we have 4 different types available. First of them is control. It is reserved for endpoint 0. It is used during enumeration. If you would like to use this for your protocol, the bandwidth is really limited. So usually this is used only for some out-of-band data. Bulk is the most common one. This is one which is used in smartphones, pen drives, network card, all what requires huge throughput. Then we have the interrupt. Interrupt has limited throughput, but the delay is constant. It means that you, when you have your mouse, because this is used usually in a human interface protocol, when you have your mouse, you would like to have your move very smooth. And that's why you use interrupt, because it ensures that the delay between your movement and between receiving the data by the host won't be larger than given value. With ISO, you have also this periodic transfer. It means that you have constant delay, but in interrupt, you have guarantee of delivery. In ISO, if the frame is received with some errors, it is simply dropped. So this one is used by web cameras for streaming video, streaming audio to USB sound card, etc. So USB device, we have our endpoints. And generally, when we are in internet world, when we have our ports, everything ends. And here, we have some structure around this endpoint to ensure discoverability. It means that we are able to discover what this USB device offers us. In internet world, we will need to nmap our host and then guess using port numbers what kind of services it provides. In USB world, we have really a limited set of endpoints, so that's why we are grouping them into interfaces, and in each interface is described what functionality it provides. So, as I told you, endpoints are grouped into interfaces, then interfaces are grouped into configurations. And configuration is a group of interfaces which can be used in the same time. Single USB device may have multiple configurations, but only one of them may be active in the same time. Endpoint 0 is the only one which is not grouped into any interface. It's always present in the device, and you don't need to set configuration before you communicate with that endpoint. And for all other endpoints, you need to first set the configuration which contains this endpoint and then try to talk with it. Okay, so plug and play. We have our device and we connect it to our computer and it just simply works. Everything happens automatically. So how does it happen step by step? First of all, you need to plug in the device. That's really the mandatory step, and if something is not working, please check that you have executed this step. Then your host needs to detect the connection. So it needs to know that some new device arrived. Then it needs to set an address for it, because by default all new USB devices have address 0, and host just choose the address for this device. Usually it will be just the first free address. It means 1, 2, 3, etc. up to 128. Then we need to get device information. We need to learn what's the layout of the device. What does it offer? Then we need to choose one of available configurations and choose drivers for interfaces. Please pay attention here that drivers in USB world are being chosen for interfaces, not for whole devices, because each interface may provide independent functionality, so it needs independent driver. You may have in single device, you may have both a pen drive functionality and network card functionality. Or in your 3G modems, there is usually a pen drive and with drivers and interface which provides the real functionality of the modem. Okay, so how the details are structured and what we can get. First of all, each device has its own pair ID vendor and ID product. ID vendor, it's a number which you can get from USB organization, but obviously you have to pay for it, or you may use any random number and see what happens. The device class, subclass, and protocol, the same triple is repeated in interface. This is a triple which identifies some standardized protocol. If your device is standard, like pen drive, this is a standard device, the protocol is set, you may just declare that you are compliant with that protocol, and this will allow you to use the generic driver. Then you have the strings, which Andrzej showed you how to set using config.fs, the manufacturer, product, serial. We have the descriptor for configuration and for the interface. Also, the endpoints are described to know what kind of endpoints we get in this interface. So, we are choosing USB driver, but what does it mean? What this USB driver really is? Well, first of all, it is usually a piece of kernel code. Obviously, there is also libUSB, which allows you to communicate with your USB device from the user space, but mostly we are using kernel drivers. So what this driver really is? Well, it's usually something which provides some interface to the user space. This interface is directly related to the functionality offered by the device, or to be more precise, by the interface. And inside this driver, what you will usually find is the implementation of some communication protocol. Usually it contains two pieces of code. First one is the code related to the USB, to the implementation of some protocol. And the second part of this driver is a piece of code which simply wraps the communication protocol into Linux generic codes. For example, to block layer or to network layer. So how do we choose this driver? This driver is described using struct USB driver. It has a matching, there is a structure for matching with most of fields from the interface descriptor and USB device descriptor. So if your device needs special handling, usually the driver will match using vendor ID, product ID, and interface ID. And if your device implements some standardized protocol, it will match using the triple interface class, subclass, etc. So how does it look on a big picture? We have our USB device over here. We have our host controller. This is the hardware part. We have driver for this host controller. We have structure which represents the USB device as a whole. We have generic driver which simply choose the configuration and create structures which represent interfaces. And then we choose drivers for those interfaces, which usually provide something to the user space, which is then used by our application. Something means network interface, input source for human interface, block device for pen drive, etc. So what's next? We provided something to the user space, and then what? Then it depends on interface type, which has been provided by the driver. If we provide the network interface, probably we have network manager who will take care of setting up this network interface. If we have pen drive, probably our auto-mount service will mount it for us and maybe show even a pop-up that new pen drive appear, what would you like to do? For mouse and keyboard, we have the input source, and by default X11 will start listening for new input events on that sources. Generally, everything on most computers happens automatically, without any user action. And that's the place which is often abused by USB attacks. So the first group is attacks which are being targeted to the USB host. The very first one, and the very simple attack for many years, was just simply to use the autorun service. It means that you place the simple autorun in file with a content to run some binary which is placed on the pen drive. Obviously, this one is for Windows, but please remember that GNOME and other also have some autorun capabilities, so it was also possible to hack, let's say, Linux this way. For now, it is disabled by default since Windows 7, so it's no longer a security threat, so that's a kind of grandfather of USB attacks. What's next? Well, when we disable such thing like autorun, then new possibilities has to be found. And we had a use case. We had some Siemens PLC controllers, which are being placed in Iran, in nuclear power plants, and we wanted to get in there. But they were disconnected from the internet. So we need some kind of transfer to put our malware inside. And that transfer was USB device. So there was a virus called Stuxnet. It used LNK vulnerability with this CVE. This vulnerability is a buffer overflow in icon rendering software. It means that when you put a pen drive and try to open the content, the icon miniatures are being generated for some types of files. And in software which generate this icon, there was a buffer overflow which allowed to execute any arbitrary code from the pen drive itself. The only action from the user here was to open the pen drive, open the folder containing the crafted file. But this is just the beginning. Then, when the software in the user space was, let's say, quite safe, we started to go more deeply. We started to go to USB protocol itself, because what we attacked previously was the user space software. And now we are trying to get some more inside attacks. We are trying to force some kernel to execute our arbitrary code. Because when we force a user space program to execute our code, then we've got only the user rights. If we force kernel to execute arbitrary code, then we've got root. So that's much better. So what we do here? Well, generally, those attacks are doing manipulation of USB communication. When you connect your USB device, before the pop-up appears, there is a lot of communication between host and the device. It's a standard communication protocol like we know in the Ethernet world. So why not just try to play with it and just try to find some holes, some buffer overflows, or some random access in it, and see what happens. Generally, there are two options. First of them is to craft the USB descriptors. For example, the configuration descriptor is being asked twice. For the first time, we ask to learn about the size, and then we allocate the buffer for this size. But then we ask for the second time, and usually we don't use the size limitation. This was the case, recent case in Windows. So you may get more data than it should be, and you may write to the memory. So this may be useful. And the second option, after the descriptor parsing, is to force load of some particular driver that we know it is vulnerable for some buffer overflow or something, and try to speak to this driver to get the code execution once again. It was popular some time ago. For example, the PS Groove. Who knows what it is? Okay, no one. So PS Groove is a crafted pen drive which allows you to jailbreak from the PlayStation 2 console. So you just connect the USB device and you get the root code execution. Now it's quite hard to achieve, especially in Linux kernel, because things are getting better and better. Especially Johan Hovold put a lot of work recently to hardening, of the USB stack. So in recent Linux kernel, it's very hard to achieve. There was even a guy who ran USB fuzzers on the Linux USB stack, and it turned out that it was quite nice. If you compare this, obviously, to Windows or to other systems, especially those embedded ones which are not running Linux. Okay, so how we can protect against it? Well, there are dedicated USB fuzzers. One of them is the phase dancer. What it is? Well, it's here you connect your host. It means laptop, the machine for the development, and here you connect your target machine. Here we've got FTDI chip and some MCU with another USB controller. So for your developer machine, it will be a kind of serial connection, and using bit banding, you will send some script which will be executed on this MCU, which will generally introduce this phase dancer to the target as different kind of devices. Using this device and this software, you may, for example, check what drivers are available on this machine. You may try to fingerprint the machine and check if it's running Linux, if it's running Windows, and then use another attacks. Or you may use some random traffic modification and try to fuzz everything and find bugs in the implementation. So it's quite useful. Unfortunately, it's quite expensive, but it's over $100, but you may get this for free on your board if it has UDC using presentation of Andrzej from about the config.fs, function.fs, etc. Okay, so now I have a short demo for the next attack. What it is? No, it's not iPad. Generally, it's tablet. Yeah? Looks like a tablet? Agree. Smells also like a tablet, so it's probably a tablet. So to my computer. Okay. Android? Android. So I will now connect this. Good idea. Thank you. Okay, so now I will connect it to my computer because let's say I'd like to take out my photos from it. Okay, so it's connected. I have some application. I don't know what kind of application it is, and I will try to click something here, but I don't know what's happening. Some terminal is being opened. I don't know why, because I'm not touching my computer. And then something more has happened. What's the point? I just connected my tablet. I just wanted to take my photos from it. So why such things happened? Let's clarify this. What you have seen here is the bad USB attack, which has been introduced something like 2-3 years ago during the Black Hat conference. Well, this attack means replacing a default functionality provided by some device which is trusted by user. Let's say tablet, let's say pen drive. It's trusted. Do you know someone who will not connect your pen drive to get a PDF from it? Come on, everyone does it. So what you can do is to replace the firmware inside the pen drive, or use config.fs and function.fs to change the functionality provided by the tablet, and instead of transferring files, just introduce it as a keyboard, and then insert a shortcut to open the terminal and send keystrokes to execute any arbitrary command with currently logged user rights. Simple? Very simple. So now let's go to another part, to the USB traffic analysis and modification. What does it mean? First of all, it's a very old attack. It means that we are not interested in getting our code, putting our code to the host machine. We are not interested in executing any code on the device machine, but we are interested in USB traffic itself. Why? Because it contains passwords. It contains both usernames, passwords, the constant passwords, for example, for bank account, but also one-time passwords. So if you are able, for example, to modify the last digit in one-time password, and when user enters the credentials, then it gets the SMS with one-time passwords, enters it to the bank account, and you replace the last digit with something other, then the user will get the message that the one-time password is invalid. And you have still your valid one-time password. So you may use it to make any arbitrary bank transfer. So this is very old. This existed even in PS2 times. Obviously, we've got the same for the USB. There is even a project, it's called USB proxy. So we may set up everything on machine like Odroid and do this just out of the box on a plain Linux. So it's generally simple. Where you can find this? Well, usually in public places. I mean, libraries, in schools, in universities, everywhere where multiple users log in to the same computer. Because it's small, it's easy to hide. Who checks the computer to which he logs in on the university? No one. How does it evolve? Well, from a simple keylogger, which is here, it evolved to bad USB 2.0 attack. What does it mean? Bad USB 2.0 is a whole framework which uses two-phase dancers to pretend as both as a host and the device. So we've got a man-in-the-middle attack. And in the meantime, we are also injecting additional endpoints, additional interfaces, modifying the traffic, the one-time passwords. We are also modifying the keystrokes to put some extra comments, extra parameters, like extra space between rm-rf/additional space, name of the catalog. But what's interesting here is that using this attack, you can get also a hidden channel from your host. Because when you have your keyboard, you think that it's input-only device. It's not true. Your keyboard has at least three diodes, caps lock, num lock, etc. And somehow those diodes are being lighted. And this is not decision of a keyboard. It's decision of your host machine. So if you are able to encode the data using these 2 bits, at least 2 bits, caps lock and num lock, then you are able to send this data from your host to the device. And on Linux, you don't need any additional rights than standard user to trigger num lock or caps lock from a command line. Another simple attack. Okay, so now let's focus on our devices. Because it's not the situation that USB host is really in risk. Both sides of the communication have this shared the same risk, because USB protocol attacks may be used also against the device itself. It means that if you connect your device to some crafted host, it may try to send a payload which will trigger some bug inside your USB stack on your phone. But why would you connect your phone to some untrusted host? That's ridiculous. Yes, obviously it is. But wouldn't you charge your smartphone when the battery is low and you have 7 hours of flight ahead of you? Wouldn't you? If you go to some airport, you will see that there may be no one around, but if there is a power station, there is a lot of people. They get together like animals to the water. So, come on, it's obvious. Sometimes you think that, no, there is no computer, it's safe, it's just charger. Here is a bench from one of Polish galleries. It's a marketing action for some bank. What it says here, it means that you can recharge your smartphone and then use the mobile application for your e-banking. Here is another example from Polish gallery. Here we even are sure that there is a computer inside because there is a screen, you may refill your account, etc. So you know that there is a computer, but you still connect to it because you need the power. So how can we abuse it? First of all, we may try to steal user data. How to do this? Well, simply just put your own device inside such a charger. Let's say, let's take the Odroid, which can be powered from the USB itself. Let's put it inside the charger. Let's put the host cable outside, and then a lot of people will come and connect their smartphones. Wouldn't they see difference? Yes, they will see difference in some versions of Android. For example, in old Android version, it's 2.3.6. It was a huge black screen. This is in Polish, sorry. I forgot to change this to the English version. But it means that your phone has been connected to the computer and it asks for agreement to provide the data to the host. Then we've got Android 4.4.2. Do you see some black screen? I don't. There is a small, here on the left side you've got the charger only, and on the right side you've got the USB host. So for charger only you will have a lightning here, and for USB host you will have both lightning and the USB logo over here. For some short time you will also have the message in the notification. So there is some difference. But if you go to Android 5.1, there is no difference unless you swipe your finger and see the message. So, and what happened then? Then we've got newer version of Android, and of course, in changelog, this is not a bug. Obviously, it was a feature, but now silently we are fixing our bugs and saying that we are introducing a new feature and making a huge success from it on Google I/O conference. So in Android 6.0 and others, each time when you connect your mobile phone to the computer, you will get a notification, a pop-up which asks you, would you like to provide the data to the host or not? So now it's safe. It's only in older Android versions that you may get this data. Obviously, one of protection method is to use your pin lock or to use your locking symbol, because until you unlock your phone, any USB host won't be able to read the data from it. So if you won't unlock the screen, then you are safe. But if you unlock it and you use one of those versions, then you may get your data being provided to some host. But is it the only option? No. There is a development protocol called ADB. Who knows what ADB is? Okay, that's obvious. So ADB is a protocol for developers to access the Android device. How does people use it? Well, usually it's simple, enable and forget. So there is an attack in old ADB version, and there are new forms of attack on which I'm working on, but I cannot share this information now. Maybe not, because I registered for some scientific conference and I had to agree that I won't provide this information until I get the results. So, yeah, for the next year. Okay, so there was a bug in ADB. The bug was relatively simple. There was no check of the return value from the setUID function. It means that if you got not enough resources, not enough there's a limit for number of processes inside for the particular user. And if you generate enough processes, then the set UID failed, and the return value wasn't checked, and you got the root console to the Android device. So remember to check the return value from your functions. Okay, summary. Remember that USB is everywhere. You use it almost every day. I believe that you charge your smartphone sometimes even twice a day. So pay attention to what you connect to your smartphone. Pay attention what you connect to your computer, and remember to check the return codes from the functions. So thank you. That's all from me. If you have time and you have questions, I will be happy to answer.
Do we have any really brief questions? No? Yeah?
What means do we have to protect ourselves from attacks like pushing something to our host, something evil to our host? Can we somehow harden our USB stacks, or what can we do more than we have now to protect ourselves from evil devices?
Okay, so there are two ways. First of them is the USB stack hardening. It's ongoing, so it's getting better and better. But for many of those attacks, the problem is automation. If you have too much automation, then too much things is being run automatically without your action. But you can limit it using the USB device and USB interface authorization. There is a USB guard project which will, for example, produce a pop-up each time when new USB device appear. You will get all the details of the USB device, and you may decide if you would like to use it or not. If you decline, then there is no driver for this device in the kernel, so there is almost no communication. But obviously, the phase for enumeration, it has to be secure enough to pass all the attacks.
Do you need some modified, some kernel mode? No?
Some kernel mode for USB
model for this, a special driver?
But for what? For
this protection?
Mm-hmm. No. It's built-in.
It's user space?
Yes. Mm-hmm. USB guard is entirely in user space. It uses the USB device functionality, which is available for a very long time. And the USB interface authorization is available since 4.2 or 4.4.
Mm-hmm.
Okay, so you know.
Mm-hmm. Thank you. Okay, so... Great. Maybe some questions afterwards.
Okay.
Will take place, and now we have to go to the next talk.
So thank you.